Okay, we're going to find a partial of z with respect to x and also with respect to y without solving for z first. So it's implicit differentiation, actually implicit partial differentiation. The key is to view z as an unknown function of x and y, so we don't view it as a constant in taking the derivatives of both sides of this equation. And so I'm only going to write z explicitly as a function of x and y here in this first line, but that's how we're thinking of z. So partial of x to the fifth with respect to x is 5x to the fourth. Partial of y to the fifth is 0. Now our partial, we have to use the chain rule because z is an unknown function of x and y, so we get 7z to the sixth times the partial of z with respect to y. Excuse me, with respect to x. Okay. Then on the right hand side we need to use the product rule because we have a product of functions of x, so we get 5y times z, which is a function of x and y, plus 5xy times the partial of z with respect to x. Okay, calculus is over in this first part now, and everything else is algebra, solving for partial of z with respect to x. So we need to get the two terms of our equation that have partial of z with respect to x as factors, and move those two terms to one side of the equation, move everything else to the other, so we can factor out the partial of z with respect to x and then solve for it. So that's what I'm doing in this step of our solution. We have 5x to the fourth minus 5yz on one side of the equation. We have both terms that have the partial of z with respect to x on the other side. And so what we will do on the right hand side is to factor out partial of z with respect to x. And then we just need to divide both sides of the equation by 5xy minus 7z to the sixth. And we find the partial of z with respect to x is 5x to the fourth minus 5yz divided by 5xy minus 7z to the sixth. Now if we had moved the terms with the partial to the other side of the equation instead of the right hand side, then we would have wound up with the negative of the numerator we have now. We would have wound up with 5yz minus 5x to the fourth, and the negative of the numerator, we would have wound up with 7z to the sixth minus 5xy. These are equivalent because they're just a fraction multiplied both top and bottom by -1, so that does not change the fraction. Okay, so there's our solution to the first part of finding the partial of z with respect to x. Now we find the partial of z with respect to y and do the same thing, viewing z as an unknown function of x and y. Partial of x to the fifth with respect to y is 0. Partial of y to the fifth is 5y to the fourth. And then we need the chain rule here, 7 times z, which is a function of x and y. It's not a constant. We don't view it as a constant, times the partial of z with respect to y. On the left-hand side and the right-hand side, we need the product rule again, and so we're going to get 5x times z plus 5xy times the partial of z with respect to y. And once more, we're going to collect the terms that have the partial derivative on one side of the equation and move everything else to the other side of the equation. Factor out the partial of z with respect to y and solve for partial of z with respect to y that way. Skip a step here and assume that we've factored out partial of z with respect to y. and leaving as the other factor 5xy minus 7x to the 7z to the sixth, and just divide both sides of the equation by the 5xy minus 7z to the sixth. And that's our partial with respect to z. And again, remember that you could have wound up with the negative of the numerator over the negative of my denominator. And that's the same solution, just expressed differently. And that's it.